Okay.
So when you are ready, I think you can start. You come from Universidad de Cantabria, Spain.
Yes. Can I start?
So it's quite a familiar instance with a few people, but we are happy to understand your results.
Thank you very much for the invitation. Also for the invitation to participate in the program. It's very nice to be here in Cambridge. So my name is Diana Stan. I come from the University of Cantabria, which is in the north of Spain, the city of Santander. Actually, I'm from Romania. I have been living for a while in Spain. So today I will talk about some estimates, called Carleman type estimates for fractional relativistic operators. This is a work in collaboration with my colleagues from Bilbao, Spain, from Spain. The problem that of our interest, so this is an evolution equation. It's a function which depends on time and space. Time is positive and space is n-dimensional. And the operator, the diffusion operator, is this s power of minus Laplacian plus some positive constant that we call m squared. And this is called relativistic fractional Laplacian, also called relativistic Schrödinger operators. It's also this name in the literature. And then in the right-hand side, take a potential multiplied by the function. And we will consider this E to be a real value function. And we will take it bound in time and space. The power S is between 0 and 1. We won't take the limit cases. Cases S is strictly between 0 and 1. And as I said, m squared is positive, so we can take m positive. And we will take it larger or equal than 0. Then I will explain what are the differences with m 0 or strictly greater than 0. The motivation for my talk is to obtain some lower bounds when the spatial variable is large, and these lower bounds, they are of this form. So the first one, we take x to be between r and r plus 1. Also here on the right hand side, maybe you can take 2r or 5r. You want to take a region in which x is more or less like r when x is very large. And then you want to bound from below this one.
Diana, sorry to interrupt you, but there is a sort of echo. Maybe you can improve the connection. Because at the beginning, the sound was perfect. Now we hear an echo.
Sometimes maybe we can change the microphone.
No, this is the problem on some participant. Check the microphones of people who are online.
It's okay to see.
Only.
Everyone is waiting. I don't know.
Try to restart.
No, sometimes there is a problem with the microphone. Like can you see what so this is echo canceling speaker. So it should be this one. Yes, that they won't hear the questions. But that's not yes.
So how about now? Is it better?
Perfect. Perfect. Okay.
Problem with the microphone. Okay, so I said that I'm interested in proving lower bounds of a quantity like this one. So this is u squared. And here we want to take some non-local gradient of u, but we have to see what this thing means. So this is just a gradient s. This is just a notation for something that we have to find later. Okay, so this we integrate, we take, this region when x is this region depending on r, and then we also integrate in time between 0 and 1. Which say that it's our interval of interest. And we want to prove some lower bound for this quantity. And our answer is that this would be larger than some exponential, negative exponential, depending to some power of r. And the other case, it's something which is not so strong. So we are also happy if we manage to prove this second one, which says that this is a kind of tail behavior. You take all x larger than r, you take this quantity, and so this is the tail of the solution in some integral sense, and you want to prove again that this is bounded from below. This result is not easy to prove since because we deal with this diffusion problem. For instance, if you take positive solutions, then when x is very large, so x goes to infinity, your solution goes to 0. So here, when r is large, this quantity, u squared, and also this gradient, they converge to 0. So even if you take this integral form, it is not easy to prove that this is bounded from below by some positive quantity, which is also going to 0. So we are interested in quantitative estimates of the tail of the solution. So we can formulate it in this form. The results that I'm talking, the results of this talk, they are contained in this paper, which is published online in Revista Matematica Complutense. Okay. So you can't see the first, why this thing appears here. Sorry. Okay, so you can see the first line. So the ingredients to prove this kind of lower bounds, we know the 3 types of ingredients. And the first one, they are called monotonicity arguments. And they say the following. Now, if you assume that the initial data of your problem has some exponential decay, maybe some integral sense, but if the initial data has exponential decay, then we want to prove that for immediately positive times, the solution also has exponential decay. So this is the first argument we need. The second one, it's called convexity type. And here this says that if you know that the solution has exponential decay at 2 different times, for instance, 0 and 1, this is written with T1 and T2, then you have to prove that for all times between these 2 fixed times, for all intermediate times, the solution also has an exponential decay, and you even want to prove that this is better. So this is called convexity arguments. And the last ones, they are called Carleman type estimates. And I will explain in what follows what the Carleman estimate is. This procedure that we are trying to perform, it's quite general since it works in many local cases. There's a misprint here. So for Schrödinger and heat equations, but local one, the lower bound that I mentioned before is of the following type. You have here a quadratic exponential. And this was proved by Escauriasa, Koenig, Ponce Vega, and many of their papers. You can also prove it for the KdV equation, and here the decay is slightly superlinear. So here you will have an exponential of minus a to r to 3/2. Also I want to mention that for discrete Schrödinger equations, the lower bound here, it has an exponential of minus some constant r log r. So this is more than linear exponential decay. Okay. So to make publicity, now we are also working in discrete heat equations, and we are able to prove the same bound here. But everything here is local. And now we want to prove this kind of results for non-local evolution equations. And this is quite difficult. I will tell you in the end what is let's say the big problem that appears when trying to conclude this kind of lower bounds like here. So this is the relativistic fractional Laplacian, the operator that I consider in this talk. We will denote it always like LSM throughout the talk. It can be defined, for instance, with the Fourier transform. So the symbol is psi squared plus m squared to the power s. So we take just the symbol of the local operator to the power s. You can define it also with a singular integral. And here you can see there appears a difference with respect to the definition of the fractional Laplacian, since here the kernel is, let's say, half of it is like the one of the fractional Laplacian, And the other half is the modified Bessel function applied to this x minus y. And then there is another correction term here. So this term appears, this M2SF, it appears since here in the Fourier transform, if you put in the symbol, if you put psi equal to 0, then you still have this term M2S. So here you will not get that when psi is 0, you get 0. Okay, so then also in the integral formulation, you will have this kind of correction term. So this is the definition when M is strictly larger than 0. As a comment, the modified Bessel function, when the argument is small, so when the argument is close to 0, this is like a power. And when the argument is large, this has exponential decay, linear exponential decay. A big problem of this definition is that you don't have a scaling invariance. So here you cannot take constants outside this modified Bessel function. And in the case of the fractional Laplacian, when m is 0, so you don't have this Bessel function, and here you just have x minus y to the n plus 2s. And so there you can take constants outside. You can have a scaling invariance. This is a difference with respect to the fractional Laplacian. There are other definitions. You can use the extension problem. You can use a subordination formula. I will not mention them since I will not use this kind of definitions here. So our motivation when we started to work with this operator, we found in the literature that many people work with this one. For instance, Carmona, Masters, and Simon, they consider with the S equal 1/2, they consider this operator and they call it relativistic Schrödinger operator. Then we even find a paper of Froelich, Johnson, and Lenzman, and they consider the boson-star equation. Again, the 1/2 power appears. Also, there is a big motivation from stochastic processes, since the relativistic fractional Laplacian, it's the generator of relativistic alpha stable processes. There are many references about it. Also, the case 1/2 appears in the book of Lieb and Loss. And now, to mention something about the inverse operator. So recall that the fractional Laplacian, its inverse is the Riesz potential, and it has the kernel has this definition here. And in the case of the relativistic one, so this is with the constant m² 1, the inverse is the Bessel potential, and this is the definition of the Bessel potential. You can find all this information in for instance, in the book of Stein or the book of Folland. Okay. So what happens with this m² that appear also in the integral definition? So if you remove that quantity here, this m2s f², you will get only this integral operator. And in fact, this is the, say, true diffusion operator. Since if you consider the heat equation associated with this operator, this is in fact an equation which conserves mass, like happens in diffusion. I mean, as for the classical heat equation, the classical heat equation has mass conservation, so you would expect that a diffusion equation also has the property. So you would have to consider this kind of operator. But working with this one is not so easy, since the composition, it looks like this. So it's not that like if you consider only this LSM, let's say only the first one, where you can compose LS with LS and you get L2S. So this is not working. For this diffusion operator, the composition formula is not so nice. So we prefer to work with the first one, and we do this observation. If you consider the equation for R, so the one that it's a diffusion equation, then you have a change of variables. So you make this change of variables and you arrive at the equation that I mentioned in the first slide. So the one with this operator, okay? So since there is a transformation between these two, we prefer to work with this last one, since the composition rule for this operator is much nicer. Okay, more details. So let's understand. We want to better understand the equation. So if you take the fundamental solution, that you take the heat equation associated, and you take as initial data the Dirac delta. Then you can obtain the fundamental solution using the Fourier transform. So the fundamental solution will have this expression in Fourier transform. And I mean, if you want to obtain Ks, this is not explicit usually. Only in the case S is 1/2, you can get an explicit expression. It doesn't look nice, but it is explicit. And there is here a Bessel function, a modified Bessel function, and you know the decay of this one. So you can have a characterization of this one. And for the S different than 1/2, there are a lot of there are many papers where they characterize this this function. This is in fact the probability density function, and there are papers in the literature where they do a characterization, a decay of this K. Okay, and for instance, we found this formula, and this is very helpful in some computations. Okay, so more preliminaries that I will need in order to give a proof of the estimate that I want to explain here. We also need this quantity, which is called the remainder in the Leibniz rule. So this means that if you take the operator applied to a product, then, for instance, if you are in the local case, so if L would be the Laplacian, no, then you will get F Laplacian G equal G Laplacian F plus 2 gradient F gradient G. So this is what you would expect in the local case. So in the non-local, if you take this quantity, so this will be a kind of gradient F gradient G, but in a non-local case, in a non-local sense, you can compute it. And you arrive with this expression. It's written with small letters to be able to put it in the slide. So you will get to this expression. The important here is that if you take FF, so this in the local case will be minus gradient F squared. So in this case, you will take FF, and here this quantity will be positive. And here you will also have F squared. So this will be positive, but with a minus here and minus in the other side, you will get that this expression is negative. So this is the equivalent of the minus gradient F squared from the local case. And a consequence of this is when you take the operator applied to F squared, this is less than 2F, the operator applied to F. This is inequality. It's very useful when we will prove energy estimates. Okay. And some other remark is that if you integrate once more this formula, you will arrive at the Dirichlet form associated to this operator. So now I want to talk also something about unique continuation. This is another motivation of our paper. So what means unique continuation? I'm sorry, you cannot see the title. I don't know how to move this thing from here. So, they see it. Okay. So I write here unique continuation. So what means unique continuation? Well, there are many types of unique continuation. Here are 4 of them. Weak unique continuation for a PDE says something like, let U be a solution of a PDE. And assume that U is 0 in some ball, then you want to derive that U is 0. This is called weak unique continuation. The next one is strong unique continuation. Here, instead of assuming that U is 0 in a ball, you assume that U vanishes of infinite order in a point. That means that U vanishes as a polynomial. Then you want to derive that U is 0. This. And the next one, in the form of Landis conjecture, this deals when your PDE is defined in all space. So you have a function which is defined in all Rn and it takes real values. So now you want to say something about how much can your function decay at infinity. That means for large X, how much you can assume that U decays such that U is not trivial, U is not 0. In some PDEs, for instance, if you assume that U decays exponentially, and here we have a power of this x to the sigma, for large X, then if this C, for instance, is large enough, or this sigma is, well, not sigma is fixed, C is large enough, then U is 0. So this is unique continuation in the form of Landis conjecture. And the next one, it's for evolution equations. So when you also have time, then for instance, you can assume that U decays exponentially at 2 different times, let's say 0 and 1. You always have to assume the initial data and then a posterior time. So if this A and B, they are large enough, or maybe there are some relation between them, then you want to derive that U is 0. So all these properties, they are very useful in order to derive uniqueness of solutions of PDEs. Because if you take that PDE and maybe if it's linear, if you take the difference of two solutions, then you will have that difference will satisfy one of these properties, and then you will get that the difference is 0. That means that your two solutions, they are the same. So this is all these properties are important to prove uniqueness. In the non-local setting, to prove unique continuation, it's very difficult. And the main problem of proving unique continuation is that you cannot localize. Usually when proving these results, one multiplies U with the cutoff function, because first you want to localize in order to be able to prove your arguments. And then you argue for this localization. And in the non-local setting, it's very difficult to do this. There are some references. For instance, weak unique continuation. This was proved by Fallen and Feli, also Barrett and Garofalo. For they do elliptic PDEs, and Barrett and Garofalo, they do this S power of the hit operator, and they all use the extension problem. About fractional Landis conjecture in the non-local settings, that was with the fractional Laplacian, there are some papers by Anca Narulan, and she also uses the extension problem, where you arrive to a local problem, and you can use arguments more or less similar to this, let's say, corresponding results in the local case. So in our paper, we give first these results. This result concerns the fractional Laplacian and not the relativistic, and we give a short proof of these results, so that this also motivates the fact that we want to work with the relativistic one. So our first result is this theorem, which says that take the fractional Laplacian of U, and this is equal to a potential multiplied by U. This is an elliptic equation in all space, and you take a bounded potential. If you assume that U decays exponentially fast at infinity, that means when x is large, you will have that U of x is less than exponential, so minus a constant. And here you have a power of x which is larger than 1, so 1 plus epsilon. Then U is 0. So if you have this decay of U, then U must be trivial. And the proof of this is it's quite short, since if you pass to the Fourier transform, then you will have here the symbol of the fractional Laplacian to S, and here in the right hand side you have the Fourier transform of this VU. And now you use the fact that U is analytic, that the Fourier transform of U is analytic, and this is a consequence of the fact that it has exponential decay. So a function which has exponential decay has a Fourier transform analytic, and since the potential is bounded, also in the right hand side you will have the same. So here you have analytic function, F is Fourier transform F is analytic, but this side to the twist, this is not analytic in the origin because it cancels. So you will get a contradiction. So U must be 0. So the proof of this is it's very fast, but this is because here we assume a superlinear decay. So if you take here 1, this is not working. You cannot prove anymore that the U is analytic. And if you want to take this one, you have to go to this previous paper of Roland, where she proves this result even with 1.
X of x, does it work?
I guess so. Yeah, it works. Okay, so in the case of, if you want to prove the relativistic fractional Laplacian, well, this is analytic, so we cannot obtain the contradiction as before. This is in fact analytic in all the, you take the complex plane and you remove in the imaginary axis, you remove all these imaginary numbers which have this lambda larger than m. So from the m above and minus m below. So, but in all complex plane minus this region, this is analytic, so you cannot do the same as before, it's not working. If you want to take the parabolic problem, even with fractional Laplacian or with the relativistic, this is not working again, because the exponential decay of U, it may not be inherited by the time derivative of U. So then you won't have that this UT is analytic. This one will be, but then the time derivative, no. So you cannot use the argument as before. Okay. So we cannot work with this problem. So there is something to study. I mean, there is a problem to solve. No? If you want to assume less assumptions decay on U, not exponential, there is a paper of Frank Lenzman and Silvestre, but they consider radial solutions, and they assume less decay on you. Okay, and then I also want to say that these techniques that I want to use that we use in the paper, and that we would like to use them in order to derive unique continuation, they may be very good to use for non-local operators that have fundamental solutions or integral kernel that has exponential decay superlinear. I mean, to have, for instance, I mentioned before the relativistic operator, and the kernel is a Bessel function, and this has an exponential linear decay, so e to the minus constant modulus of x. So if you know any non-local operator that has an integral kernel which decays more than exponential, so exponential to the minus x to some power, this would be very good to, let's say, to use with all this kind of program. So I would be interested to collaborate. Okay, this was a kind of publicity. Okay, so now let's go to the heat equation with the relativistic operator, since we gave so far the motivation to study this problem. Okay, so our purpose, well, it is to prove that kind of lower bound that I mentioned at the beginning of the talk, and that lower bound will be useful to prove a kind of unique continuation result in the form of uncertainty principle. And this will be based on assuming exponential decay on U and then deriving that U is 0. So this is our purpose. And in this talk, I will only tell you about the estimate that we need in order to be able to work with the proof of this uncertainty principle. Okay. Also, as a consequence, we can derive some results concerning stationary solutions. Okay. So and now I will explain about monotonicity estimate. So if you take the heat equation, first let's take it without potential, so that I can explain better the reasoning. If you take the heat equation without potential and with initial data, then you take this quantity, and this is called a weighted energy. And on omega, this is the weight. It depends on time and space, and it is a weight that we want to choose in order to have that this energy function is monotone decreasing in time. So we compute the derivative. Okay, so this is the derivative. You put the derivative in time inside the integral, and then you organize the terms, writing here that ut it's the minus the operator applied to u, integrate by parts. So then you arrive to this formula here, and here you obtain this reminder of the fractional Leibniz rule. And as we saw in the definition, this was negative. So now you have this term here. So you want to take a weight such that this term here is negative. If you manage to do that, then you will have the derivative of h is negative, so that h is monotone non-decreasing, non-increasing, monotone non-increasing in time. Okay, and then we want to prove more. We also want to have some convexity results, so that we compute the second derivative of h. We do so again, we organize terms, and we arrive to this expression here. So again, we will have a term here which is negative, another one here which is in fact this is positive, right? This is positive because there is a minus here. This one is positive. So now our problem is this first one. So we need a proper weight.
Omega is always positive.
Omega is always positive. So now we need to find a weight which is positive. Okay, so I want a positive weight so that h is positive. Then I want the first derivative of h to be negative, so that h is non-increasing, so that h of t is always bounded by h of 0, so that it is well defined. And then I want h two derivatives, so to that, to be positive, because this means a convexity result. Okay, so what is the weight? And the weight that we managed to use, in fact, it's a separate variable solution to the heat equation. It is based on the fact that you can construct eigenvalues of this fractional relativistic operator, and they are just the linear exponentials. So e to the lambda x, this is an eigenvalue of the fractional relativistic operator, and this is the corresponding eigenvalue. This was quite nice because in the case of the fractional Laplacian, so when m is equal to 0, you don't have this anymore. You cannot use the exponential since the fractional Laplacian is not well defined with exponential functions. But the relativistic one with lambda less than m, it is well defined. Using these eigenvalues, you can construct separate variable solutions, and they solve this. Well, this is in fact the heat equation for the fractional relativistic backward because of the minus. Okay, so with this weight, we can prove that h dot is negative and h2 dot is positive. Okay, so first derivative will give you that h of t is less than h of 0, so h is well defined. And second derivative positive will give you this convexity estimate that says that h of t is less than, and this is the convex combination of h of 0 and h of 1. And this is useful because this result says that if you can control, if you can estimate what happens with the energy at time 0 and time 1, then you can estimate what happens with the energy at all intermediate times between 0 and 1. Okay, and this is log convexity. Even you can even prove log convexity. That means that the logarithm of h is convex, and this gives you in terms of product. As a consequence, as I said, you can derive uniqueness of solutions. That means if the difference of two solutions, which is also a solution at time 1 is 0, then u is 0. So your solutions are equal. Okay, so this is what happens when your potential is 0. And now let's take a potential. So I call it f instead of call it u. I call it f. I put a right-hand side term. Again, I take the weighted energy. And again, I do the first derivative. Everything is as before, but you also have this term appearing here, which contains the right-hand side term. Okay, so now, so we want to estimate this. We want to work more with this formula here. So now I will impose some conditions on this right-hand side term. I will take it to be in the weighted L2 space. So with this exponential weight, and also I will take an initial data to be in the weighted L2 space. Then the weight that I need here, it is inspired by the previous one. Also, it's a separate variable solutions, but I put here a capital A because this is will be a parameter that I can make it larger if needed. So I take a similar weight as before, and my energy estimate that given by the fact that h dot is negative, and when I say negative, it is that this first and the first integral and the second one, they will be negative, but you will have a correction term given which is a consequence of this right-hand side term appearing here. So our energy estimate in this case is this one. So here you have your h. This term is positive because the h was negative. So this is your energy term. And here is the upper bound. So this is your energy at time 0. And this is a term which is caused by the right-hand side term of the equation, the right-hand side of the equation. Okay. So this is called persistence of the exponential decay, because this says that if this one is finite, which contains the initial data, and the right-hand side is also finite, then the energy at time t larger than 0 is also finite. That means that you also has exponential decay. No, exponential because we take omega, the weight, to be exponential. So if you have exponential decay at time 0, you will have it at all posterior times. And this is one of the ingredients that I mentioned at the beginning of the talk. Okay. So now I want to talk about the convexity ones in the case where you have a right-hand side. So I do the same as before. I take the weighted energy, and I have the h dot, which is this one. And now I want to take another derivative of h. But the problem is that I cannot just do derivative here. I cannot take h2 dot because I cannot differentiate this term. The right-hand side, it's only an L2 function, but in a weighted L2. But I don't know that f has a derivative in time. So I cannot do a derivative of this term. So the trick now is that to denote this first one, for instance, d of t, and you do a derivative of d of t. So not of the whole h. So you do d dot, you arrive at this expression, which will also have some terms with f. And now, in order to obtain convexity arguments, that means in order to characterize from this d dot to have an estimate for h, you have to integrate back. So in the case where you don't have f, this is just h two dots. So you integrate twice and you go back to h. But when you have this d, you cannot just integrate twice. No? So this is the trick that you do. You write this expression. So this is the derivative of this parabola, which is concave parabola, which is 0 at 0 and 1. You do this, multiply by h dot, integrate. Okay, and this, if you integrate it by parts, you arrive to this this expression here. Okay, so you put the derivative in the derivative of h, you put it on this left term. So you arrive to this expression. But now if you integrate by parts in the other way, that means you take the derivative on the other side. First, you need to replace h dot by d plus this term. And then once you replace it by d, you integrate by parts and you put the derivative of d only in this first term. And in this second integral, you don't do anything. So then you put the derivative on d and you have the derivative of d, which you have computed before. Okay? So now you're replacing with the proper weight. You arrive to this kind of convexity arguments, which says that if your weight is this one, separate variable solutions, then this is your energy. Okay, you have to multiply it with this term depending on t, then plus positive energy terms, and this is less than the energy at the sum of energy at time 0 and 1 plus something which involves the right hand side. So this is the f, but instead of writing f, I write the operator. Okay, so I write the operator and I write the estimate in this form. The advantage of writing in this form is that I don't have to say here that u is a solution of the PDE. So with the estimate written in this form, I just say that u, it's a function in L2. Okay. If I also say that it's a L2 energy function, this, for instance, can be derived by the energy estimate when u is a solution on the PDE. But let's just assume that u, it's a function which belongs to the L2 energy space. L2 space. So then I have this left-hand side term, which is the energy, and in the right-hand side term, I have the operator applied to u squared. So also with the same weight. Okay, and the estimate written in this form is called the Carleman type estimate. So this says that the weighted L2 norm of the operator applied to u is bounded from below by the weighted L2 norm of u squared with some coefficient. And the coefficient usually is very important since these arguments of unique continuation type, usually they are proved by playing with the exponents in the weight. This is the trick. These exponents in the weight, they are very important since you can, for instance, you can make it larger, you can take them to the endpoint case, and they help you in order to derive some kind of contradiction when you want to prove the unique continuation. So this kind of estimate is called the Carleman type estimate. Okay. Well, this one maybe I will skip it since it's more technical. Okay, so this is the main estimate of our paper, and now our work in progress, let's say, it is to be able to use this kind of estimates in order to derive unique continuation. So the program to derive a unique continuation, it's something like this. You assume that you have a non-trivial function, and for instance, you assume there is some mass close to 0. And then you must be able to prove this lower bound. This was the lower bound that I mentioned in the first slide. You must be able to prove this, and our ansatz is that in the case of the relativistic fractional Laplacian, the exponent that you can prove here is this one. This is our ansatz. So now we are working in this, but it's not working so well. And the problem is that when you want to apply your Carleman inequality, so this one, but not to U, but with U multiply, but with a cutoff function, because you always need to localize this kind of problems. So we are not able to make a good characterization of an unlocker operator applied to a cutoff function. And what we would like to do? We would like to have some part of the operation of the operator applied to U, plus something which would contain this kind of term appearing in the lower bound, and then all the other remaining terms we would want them to decay with R, and this is not so easy to prove. So how can you characterize an unlocker operator applied to a compactly supported function? How can you say about that? Can you prove it decays, and how much it decays? So this is one of our problems now in order to be able to conclude this this lower bound. So this some ideas of the problems. Also, if you want to ask about why we don't use extension problem, well, this is not so easy, since if you deal with an evolution problem, when you do the extension technique, you will get some kind of dynamical boundary conditions. It is not easy to work with them. Well, that's all for my talk. Thank you.
Thank you, Diana. Are there questions or comments from the room? You can ask directly, while if someone online.
I have a question. So I don't see from the calculations on the slide, but how important does it seem that this is the case of the relativistic stable operator? So for example, if you not only look at the alpha stable or the relativistic stable, but this, let's call it a Riesz-Bessel operator.
Yeah.
Or if you look at the sum of two fractional Laplacians, would the same technique go through?
A sum of two fractional Laplacians? I don't know. I have to study first the heat equation associated with the sum of two fractional Laplacian, and to see how it behaves, how we could get their fundamental solution, the decay, because this will give you an idea about what you want to prove. Yeah, so I didn't work with the sum of two, but it's an idea. I could think about it. Yeah.
Other questions or comments? You use these bounds for a specific goal. Do you think that your bounds can be useful also in different instances for different goals?
I think they can be used to obtain uniqueness. So the purpose of my talk was, I mean, of my project is to arrive to this uncertainty principle using quantitative lower bounds. But if you just look at the convexity estimates that I mentioned, maybe it's useful to derive uniqueness for the PDEs when you have two solutions which may have some more properties, let's say. If you
And how about using them for approximate solution?
What kind of approximate solution?
Let's say substitute your term with its bound and approximate your solution with it. It's not feasible.
I don't know. So if you approximate your solution, what happens with the approximation? It is still satisfying the PDE?
Yeah, if you want a different PDE in which you have an approximation. But maybe it's too naive idea. Maybe it's too naive. It's not my topic, so
I have to think about it.
Yeah. Any other comment?
Can I make a small comment myself?
Yes,
I'm
sure.
Joseph, you cannot see me, but
Yes.
I think that one thing that you can use this type of argument for is to prove also that certain solutions cannot exist. So if Diana would like to go back to the very beginning, more or less, where she was listing unique continuation type of statements, then I think it is
This one.
visible from it, yeah, more or less here. It is more or less visible from here that, for example, if you look at the Landis conjecture, that if you have a particular decay of the solution, which I think would be something like the eigenvalue equation, for example, then U has to be zero. The solution has to be identically zero. So that just means that unless you would like to have a non-zero solution, you cannot have this type of behavior. And all this type of business, like unique continuation in the weak or strong sense, and the related things and the Carleman estimates that lead to this, that Diana was explaining, they also can be used really a lot to prove that there are no solutions of particular type. Or that, for example, there exist no eigenvalues, no zero eigenvalues, or no eigenvalues of a given character. For me, this is interesting. Unfortunately, I cannot now speak to Diana. I was working on this myself for some years, but I think that she knows anyway, and this is just a small comment.
Okay, thank you.
Thank you. Other comments? No, then we thank you again. And I think this is the last of our seminars of Monday, and that was nice to close with your one. Thanks again. And
Thank you
thanks
very
to
much.
all the speakers that gave their talk in previous days, previous Mondays. Thank you.
Well, if I'm the last one, I also want to thank to the organizers for organizing all these seminars. So maybe we can clap for the organizers.
Thank you. I think we can leave.
Okay.
Bye.
Bye.
Bye.